Okay, welcome everyone. Very happy to have Pravesh with us today. Pravesh is a faculty at Princeton, and
Just click on this move.
I've only joined Princeton once in my life. He has joined it twice, both as an instructor and as a faculty member. We joined in the same year, the first time, and he taught me courses on sums of squares and algorithms. So anything I don't know about that is on him. Today he's going to teach us about positive semidefinite matrices. So what do you? And if I don't learn this also.
Actually, let me first remove all blame from me. The slides are by Raghu Meka. Okay, this is recorded now. So all the errors are of course Raghu's.
Yeah, okay. Actually, when Raghu came here, he didn't know me. We went at the guest house, and he said, I asked him, "What are you?" And I said, "Same." It's being recorded.
Okay, great. Thank you, the other Raghu, for the great introduction. Thank you all for coming to the talk, especially at whatever unscheduled hours. So yeah, I want to tell you about this recent work on sparsifying sums of positive semidefinite matrices. It's actually joined with a very young student, Arpon Basu from Bombay. He went to Bombay. And Raghu Meka, that all of you know, and Yang Liu, who is now at CMU. Okay, so first, I feel like I can more or less explain to you the whole idea here. So one of the small opportunities usually you don't get one of the opportunities, but I can tell you all the idea. It's very simple. Hopefully you like the problem, and you can think of like the main goal of the talk as asking you a nice open question that I really think is very interesting, but I don't know how to. Okay, good. So let me start with like motivation, and that's basically like a problem that many of you might have heard about. If not, like let me tell you like this relation theorem that we know. Okay, so the motivation is like can you make a graph smaller in terms of number of edges while preserving some of its relevant problems? This idea, this problem is called graph sparsification, and maybe the most well-studied notion of sparsification is when you want to preserve, let's say, all cuts, right? Like, so you want to make a graph, let's say a super dense graph, you want to approximate it by one with very small number of edges, hopefully near linear, in a way that all the cuts have the same relative size, okay? Now, of course, like, if you make the number of edges drop, let's say, from n squared to about n, the cuts are going to become smaller in absolute number, but you are allowed to wait here. That's it, okay? And, the initial motivations for these came from algorithms.
So the weights have to be the same across the. The weights have to be the same across.
No, they don't. Yeah, and this is important. Okay. Otherwise, you can't quite get many of the results that you know.
Oh, yeah, I know what I'm doing.
Yeah, exactly. Yeah, and yes, so that's a good cue. Please feel free to stop me, interrupt me, whatever, right? Like, let's make it interactive if we can. So yeah, the initial motivation for this problem was like fast algorithm. If I could somehow approximate a dense graph by a sparse one, and while preserving quality of approximation, whatever, then I could basically run my algorithms on the smaller graph and therefore speed them up. This was the initial motivation. And so here is a really fantastic theorem that kind of came out of this line of work. I'll start with the more general thing, even though I talked about cuts. This theorem already proves something stronger. It's not the first theorem in this direction, but it's the one I want to begin with. Okay, so this is called the spectral sparsification theorem. It was first proven by Spillman and Teng. There's a super simple proof of it due to Spillman and Srivastava, and versions of that can be found in many courses now, including Akash's. So what this theorem says is that every graph can be approximated by a weighted graph with order of n log n edges, okay, such that the Laplacians are approximated in the Lerner ordering sense up to 1 plus minus epsilon. So what this inequality over here means is that every quadratic form of LG is close to, within a multiplicative 1 plus minus epsilon, the same quadratic form on LH, H being the approximator. And okay, I guess the theorem doesn't appear here. I'll soon tell you the bounds here. But basically, in spectral sparsification, you want this inequality to hold for every quadratic form. Okay, and the way to relate it to cut sparsification, if you don't already know, is that if I take quadratic form of Laplacian of a matrix, Laplacian of a graph on 0, 1 vectors, then you think of the 0, 1 vector as the indicator of a subset of vertices, then this literally gives you the cut, the size of the cut, number of edges cut, or the weight of the edges cut. So, in that sense, this generalizes cut sparsification. But of course, you want this inequality to hold for all the quadratic forms, not just 0, 1 vectors. So it goes a bit beyond cut sparsification, and that's why it's called spectral sparsification. The definition makes sense here? Yeah. Okay, good. All right. So, yeah, so it definitely, this kind of a approximation definitely preserves cuts. The example we started with, but it also kind of approximately preserves eigenvalues, eigenvectors, and so on. And this turns out to be important because there are applications to speeding up algorithms for solving linear systems that rely on this spectral approximation notion. They're not, the cut sparsification notion doesn't suffice. So even in the initial days, Bencher and Carter asked this question from the perspective of cuts because they were interested in speeding up algorithms about cuts, min cut, max cut, etc. And then, later on, Spillman and Teng are the ones who realized that if you have a stronger guarantee of spectral sparsification, then you can speed up solving linear systems of certain kinds. So that was their motivation. Anyway, so there's a bunch of results. Some of them I already mentioned. The one I want to maybe highlight is this kind of culmination of this line of work. So to Batson, Spillman, and Srivastava, a really cool paper that shows that every graph admits a weighted sparsifier with order n over epsilon square edges. In fact, the constant in big O is also known. They're called twice Ramanujan sparsifier, so we know it's exactly 4. So it's a super sharp result that shows that so of course you know that omega of n over epsilon square edges are required. In fact, 2 n over epsilon square are required, and they give a twice Ramanujan bound or 4 n over epsilon square bound. We don't think, I don't know what the status of that factor 2 there is, but basically it's as sharp in some sense as like 1. Okay, so this is like the starting point of the talk. It's a motivation, so to speak. This is not what I was talking about, otherwise it could end it here. Okay.
What about verifying sparsifiers?
Yeah, excellent question. This is the segue I really like, even though this is not part of the talk. The cut sparsifiers are not verifiable efficiently as far as we know, right? Because I don't know how am I going to check all cuts. But spectral sparsifiers are easily verifiable because, well, it's a spectral inequality, right? Like you just have to compute, just whatever, like multiply LG to the -1/2 on both sides of LH and check that the largest and the smallest eigenvalues are at most 1 plus epsilon and at least 1 minus epsilon. So, yeah. So eigenvalue computation gives you a way to verify spectral sparsification. One of the happy accidents here. Any other questions? Yes.
The question asked before. You'll have weights on the.
Yes.
And how large are the
Very good question. The weights can be very large, and the example is what Raghu was pointing out earlier. So think of like 2 clicks joined by a single edge, right? Like, so that edge first point cannot possibly be dropped. But also that edge is serving as, in some sense, the only thing that gives you something across, like let's say n over 2, n over 2, right? So you need to make its weight be like polynomial in order.
Yeah, but still, no, I want to know if the representation of the sparsifier will still be order n over epsilon square. Or
Yes.
Somehow the weights.
No, the weights are polynomial.
Polynomial.
Yeah. So in fact, the representation would be logarithmically many bits in each term. You don't even need like polynomial units. Right? The table of an exponential will still be efficient, but this is going to be logarithmic. Yeah. Any other questions so far? Okay, excellent. All right. So in order to motivate the question I want to study today, which is going to be a generalization of what we just looked at, I want to view the graph sparsification problem as follows now. I want to observe that you are sampling edges. You're keeping a subset of edges. Okay. And if you've seen this before, the Laplacian of a graph is the sum of the Laplacian on each edge. It's an additive quantity, which makes sense, right? Like cuts are additive. So you should have expected this. And in particular, the Laplacians of edges are rank 1 matrices. Okay, you can even, it's very explicit, right? Like the Laplacian of the edge ij is simply like at the diagonals in the ith and jth point place +1, and in the edge, the 2 whatever equivalent places place -1. That's the rank 1 matrix that represents the edge Laplacian. So it's a sum of rank 1 matrices. So you can think of the problem of graph sparsification as taking a sum of the edge Laplacians and then keeping some subset of the edges, weighting them, so that the resulting weighted sum of some subset of edges is an approximation to the one you began. Okay? So in that sense, it's a question of sparsifying a sum of rank 1 PSD matrices. Okay, does it make sense? The reason I say this is because this is just a natural generalization. What happens if my matrices are not rank 1? Which is going to be the topic of the day. Okay, so here's the question we're going to be interested in. You're given arbitrary positive semidefinite matrices, A1 up to AM, n by m matrices. They have the sum. That's the object we want to approximate. By keeping a few of these constituent sums. Okay, we are allowed to weight them. So we want to introduce non-negative weights SIs. We want to make the weight vector sparse. We're going to keep only a few of the AIs, such as the weighted sum is a 1 plus minus epsilon approximation to all quadratic forms. Question make sense? Yeah, that's the goal. And the question is like how many SIs are needed. Okay. Good. So the answer turns out to be actually also easy. It turns out that, in fact, so I mentioned this n log n result due to Spielmann and Srivastava and Spielmann time earlier. That result essentially word for word generalizes without the rank 1 constraint. So this question was solved even before I asked it, long before I asked it. And it turns out that you can even take this n over epsilon squared type guarantee that Bass and Spielmann and Srivastava proved and extend it to this set. This requires a little bit of work, like some non-trivial new ideas, but still basically a generalization of the BSS type method. So even this question is solved. Okay, you have just as good a result, apparently, as graph sparsification. You can still get n over epsilon squared. Okay, except the key question for the talk is this as good a result as it possibly gets? I now want to give you some intuition that maybe you should expect a better than n over epsilon square bounds for higher rank matrices. Right?
You want to bound on how many SIs are non-zero.
Right.
How does that translate to the terms in your sparsifier?
So this is the same as saying that I want to choose a small number of AIs, weight them so that the weighted sum is a approximation.
Okay. Sure.
Right.
So that part I understand.
Yeah.
But the theorem says something about like when you say terms, you mean
It just means sparsity of S.
Oh, I see. Okay.
I asked.
Okay.
Yeah, sorry, I'm switching between two different ways of describing the same. Yeah. Yes.
Question.
Yes.
Is there an efficient algorithm for this?
Yes.
So it's exactly the same result.
Exactly the same result. Yeah. In fact, I'll give you the algorithm. That, in some sense, we are analyzing the same algorithm. We're just proving a better guarantee of. Right? It's the rest called sample. Yes.
Here there is nothing to say about the n value, what it will be, A1 of area.
No, M is exactly what n over epsilon square is. M is the, my bad. M is, in the way I've written it over here, M is like the number of AIs.
Yeah, so in a graph first, in the cut first, we know M is equal to n square.
Yes.
Here we have no bound on.
Yes. And it still works.
Oh.
Yes. Yeah, good observation. Yeah.
But the sense that if M was very small, this is not giving us anything meaningful.
Yes.
Yeah.
But what he's saying is that, in the case of graph classification, M is always at most n squared over 2, because that's the total number of possible edges. So here it could in principle be like infinite.
Yeah.
I can still bring it down to n over epsilon squared. Yes.
In graph sparsification, are you allowed to add the new edge?
Yeah, great question. That version of the problem would have made sense too, but we don't. In the results, we don't need. Okay. In the question I'm asking, it won't make sense to allow importing new PSD matrices because you would import the sum. Okay. So in the graph classification case, because you're sampling edges, it makes sense, but you don't need. It turns out you can always take a subset or subgraph of the original one with weights, and that's suffices. Good question. Yeah. All right. Okay, so what are we after? This question also seems solved. Story of research life. Try to find another one. Okay, so let's, in order to understand whether this is a good bound, let's try to understand why is it. Okay? And then we'll try to maybe see if that argument applies to this general setting that we are interested in. So in the case of graphs, clearly omega of n fix epsilon to be a constant. In fact, like I implore you to think of it as like point for the rest of the talk. Okay. then, basically order n is the bound we have. And notice that, you need n minus 1 edges at the very least. Because imagine that the graph is connected without the loss of generality. If you choose less than minus 1 edges, there's going to be a cut which is 0. So there's a qualitative violation. There is the graph is disconnected. If you have fewer than n minus 1 edges, so of course you need at least n minus 1 edges, sparsified. Okay, that's good. But now imagine that your graph is not random. Like, your edges is not an edge double sampling or edge sparsification. It's like, this more general PSD sparsification. Now, you might expect that this argument doesn't work. Let me give you an example. One way to think about higher rank matrices is that you're sampling multiple edges at once. In fact, the example is, all right. Yeah, exactly. Now imagine they're very high rank. Just to see if whether this n over epsilon square is a good bound or should we have hope for better. Okay. So imagine that AIs are, huge rank. For example, imagine that AIs are Laplacians of perfect matches. Okay. This is a motivated example that is going to come up later on in talk 2. If we have let's say n over 2 edges, the rank is going to be at least n over 2. So now I'm sampling like omega n rank matrices. Each matrix gives me many edges. Now this connectivity, obstruction no longer applies. Right? Like each one is giving me many edges. Higher rank is like somehow giving me more per AI. So maybe omega n is not the right answer at all. You'll soon see why this is relevant and why there is at least one interesting application. But I want you to again start thinking of the fact that maybe n over epsilon square is not the right thing. We should really be asking for something that maybe depends on the rank or some other quantity related to the AIs. Does that make sense? Okay, good. So, just to lay it out there, this is our main question. Given a family of PSD matrices, A1 through AM, and now we are going to. So notice that we have to go for something which is instance specific because AIs could be rank 1, and then we know that things are not improvable beyond n over epsilon square. So we're going to fix a family of A1 through AM. We want to describe what about this family governs the size of the minimum sparsifier. That's the question we're going to be interested in. You can think of it as like an instance-specific control of the sparsifier size. And hopefully there is a parameter like this connectivity parameter or like, this number of edges required to make the graph connected that somehow controls this quantity. This is our goal.
So if you were not working with a fixed family of PSD matrices.
Yes.
Given an arbitrary, is that what is called the PSD rank?
No.
PSD rank is something else.
PSD rank comes up in the context of extended formulations, mainly semidefinite extended formulations, and that relates to like, minimum semidefinite description of a potato. So that's very different. Yeah. I mean, I guess it has linguistic similarity.
What is the answer for a random subcorrection? I mean, like, if you just did something, if you just pick these at random.
What would that mean? What would random mean?
No,
I want to aim or random.
Yeah, but what is that?
I want to sample a sparsifier.
That's what you mean. That's what you mean.
If I have to do that, how does that process somehow suggest an answer to it?
Retaining a subcollection at random.
Because this is sort of what PSs also do.
No, it cannot work that way. It has to do important sampling. It cannot.
No, that's what by random I'm okay with assigning some importance to different things.
Yes.
And then picking up.
Yes.
Yeah.
That's the algorithm we're going to analyze.
Okay.
That is exactly the algorithm we're going to analyze.
Okay.
Yeah. Good. So, I guess I've given a bit of punchline in the sense that it cannot possibly be a little n, in the sense that the higher rank hopefully helps. And you can see that this question, as I phrased it, generalizes the graph sparsification question. Just fix the A1 through AN to be the edge Laplacian. Every graph is like, a subset of some of these sums. And, for graph sparsification, this connectivity threshold or connectivity parameter governs the sparsifier size. We want an answer similar to that. That's what we're hoping for. Okay, good. So now, at first I gave you this hint that perhaps high rank is supposed to help, but it turns out that rank itself is not the right measure. Okay, it turns out that, so maybe I don't have it stated over here, but basically there is an example. In fact, there is an example of just some perfect matchings I can create. about n of them on n vertex graphs. So I get a very, very dense graph. And I can show you that dropping any single matching would make the graph disconnect, would screw up some cut. So there is a way to build an example, even with like perfect matchings, where you basically need all of them in an n squared size graph, n squared over 2 size graph. So there is basically no sparsification possible if you just thought rank of the matrix itself was somehow related to the parameter required. Okay, so it's going to be more nuanced, and answering that is the goal of the talk. So I'm going to define this parameter for you, and what I'll try to argue is that this parameter controls the sparsifier size. Okay, so I'm going to call this the connectivity parameter because I'm trying to generalize this notion of n-1 edges being required for a graph to be connected. So the connectivity parameter for a family of matrices A, A1 through AN, script A, right? At alpha, so there is this extra parameter alpha. We'll soon see why that is needed, but for a second, ignore it. Is the smallest integer k, such that if I give you any k elements out of script A, okay, then there is some AI in this list that I can dominate by the sum of the rest. Okay, let me explain the analog to graph so that you see why this is not unnatural. Okay, if I give you any little n in an n vertex, look at the collection of all edges on n vertex graphs. If I give you any n edges, there is going to be a cycle. Okay, and then one property of a cycle is that I can remove an edge from that cycle, and I still have a path between the two endpoints of it using the rest of the edges. Okay. In Laplacian terms, if you just think of what this means, it means that the Laplacian of a single edge is dominated by the sum of the remaining. It requires some scaling here and it requires short cycles, but intuitively that's what's happening. Okay, so there is some redundancy. Does it make sense? Like any size k subset of this script A has redundancy in the sense that there is some matrix I can dominate by the sum of the rest. Now it turns out that the domination is not literally by the sum. I need some scaling. The scaling is this column.
But this almost sounds like rank, right? If I give you, no, I'm just saying.
Yeah, go for it.
If I say the rank of the over in K, yeah, but if the rank of the system is at most K,
Yes.
then as soon as you have, or less than K,
Yeah.
then as soon as you have K different things,
Yes.
you can express one of them in terms of the other.
So think about the case of cycles, and you already see that it's not about time. Okay, so you can have short cycles. You can have even on n, if I give you 100 n edges on an n vertex graph, then there is a log n length cycle. These log n edges don't define like a full rank matrix, but I can still cover one by the rest. So the intuition is reasonable, but it's not exactly about. Okay. Does it make sense? Does it feel reasonably motivated in the sense that I hope you see it internalizes the notion of redundancy in connectivity in graphs?
If you want to generalize that, shouldn't you have some, instead of summing out all the t minus I, you should have some subset of t minus I?
That's sufficient. I mean, this is only better.
So what is this sign? It's pointwise land. What is the sign?
This is PSD ordering. So all quadratic forms on the left hand side should be dominated by the same quadratic form on the right hand side.
Okay.
So the previous comment that you just made, that
Yes.
you take 100 and then you it will see a short cycle.
Yes.
But I'm trying to explain to that comment, I did not get.
So the log n, if I have a very short cycle, they don't span the whole n-dimensional space at least. Like it only spans like a log n-dimensional. I'm just trying to say that it's not about rank. You can have like this local covering property without either of the matrices being full rank or the sums being full rank, etc. But yeah, so the connectivity threshold is the minimum case, is that for every subset of k elements out of script A, one of them is redundant in the sense that I can cover any quadratic form of one by the sum of the quadratic forms in the same vector of the rest. Does that make sense? The definition? Yes.
I understand you need something like this. But
Yes.
What you never mentioned is what is the role of this alpha over here?
Yes.
And why do we have one single alpha that works in?
Yeah.
Shouldn't it be dependent on the size of T or something?
Yeah.
What's the-
So like, there is, so in some sense, the intuitive goal is to relate this quantitative notion of sparsification to something qualitative. Right? Like this connectivity parameter about graphs is a qualitative notion. It's like 0 versus non-zero, there is no numerical thing attached to it. Here there is, and you are right to like question, why do I need this alpha thing?
No, even for the cycle case, there's a notion of weighted thing, there is edge, that's what you need.
Yeah,
You can't just say, you can't have alpha to be 1 possibly over
Yeah.
there.
right? Because, if, just think of the cuts, right? Like,
That is true.
yeah, so in the case of graph, which is really a combinatorial thing,
And
right?
alpha could be just sort of.
Yeah, here it turns out to be necessary simply because like, we are dealing with two terms, like it's not a combinatorial problem.
But why the same alpha for every possible T and this one? Why not,
Yeah, in fact, it's going to be a fixed constant, like it's entirely an artifact of a proof at this point,
oh, okay.
right? Like, we don't even know, it's like something like 0.7, whatever. And that's just because our proof doesn't give one.
Okay.
Yeah, so maybe it is a little bit surprising, but you'll see the proof, it's very transparent.
So one more.
Yes.
So just for standard graphs,
Yes,
all the AIs were just edges.
yes.
Then, if I were to just take a cycle, this
Yes.
alpha will turn out to be something like.
One over alpha will be length minus. Length of the cycle minus.
So look at the cycle. Okay. Look at any quadratic form of one of the edges.
Yeah.
It's either 1 or 0. Let's just look at cuts for example.
Yeah, so the other side could be potentially as large as n.
Yeah, but I just want the domination. It's a one-sided
Oh, I
inequality.
see. Okay.
It's a one-sided inequality. I just want the right-hand side to be larger. You see what I'm
Like
saying?
I say, it is no more, I mean, it's within a one of, like a root n type thing, but we don't care about that one.
This part,
Yeah,
in
yeah.
this case, we don't care.
Okay,
Yeah.
I see.
So sort of getting for any sort of cycle of T, taking T as a cycle,
Yes.
any subgraph of T,
Yes,
there is some edge of weight alpha that you can remove and it will still remain T.
correct.
That's what.
That's one way to think about it. But you should notice, this comment or emphasis is important in the sense that, this is not any notion of specular approximation. It's a one-sided domination. The right-hand side can be much larger in principle. Like, so otherwise it would be senseless. Like, I would be characterizing sparsifiers by sparsifiers. That won't be meaningful. So it is somewhat qualitative. Okay, it's only one-sided domination. Any other questions about this definition so far? Okay, great. So so the main result is that this parameter is basically going to control the sparsifier size. So what we will prove is that if I have m matrices in little n dimensions, then up to a log n times log m factor. So this log n is log of the dimension of the matrix, log m is the log of the number of the matrices. Up to that factor, this n star quantity, I should have said, n star is simply like for some fixed, like fix alpha star to be some fixed constant, right? Like, so that's what n star is. Now alpha goes away. Okay, so that controls the size of the sparsifier. In fact, we are going to give an upper bound in terms of n star up to some log n factor.
You don't know how n star behaves, n behaves with respect to alpha. You're just fixing alpha to be.
Yes,
some
that's
constant
right. Yes,
from now onward.
Yeah. So I'll tell you why I do it in a second. But so that's the upper bound, and it turns out that n star is necessary. Okay, so this theorem basically says that up to this log n times log n factor, n star characterizes the size of a sparse.
So your notion of redundancy is kind of like spot on.
Well, up to this log n factor, right? Like, you could ask for more spot on measures, but right now that's what it is. Right? But any question about the result?
You have a log n times log m.
Yes.
Not just a log m with.
Yeah.
Okay.
So you should think of it as follows, like, because we are doing importance sampling, the algorithm that Ramprasad was saying, log n somehow is necessary. It's a coupon connector law in some sense, right? Like, imagine like, just picking things at random, like, imagine like scalar sparsification, right? If I have n things, they're all equal weights, I still want to cover all of them, I need to take n log n. So that log of the number of things I have is necessary. So log m is in some sense just importance sampling. You can't hope to get rid of it. You could say that log n should not have been necessary. Or like, in principle, you could imagine that there is an argument that doesn't lose log n. We don't know.
So the easiest thing is deterministic.
Yes.
That just look at the
Yeah.
resolvent.
Yeah, so you should think of this as the analog of Spillman-Shrivastava or Spillman-Tech. So the natural open question is there a BSS analog or MSF? Yeah, but yes. Any
If
other?
you shave off the log n,
Yes, we have, because these are three long. I mean, I don't know which one, but one of them has to be there in the sampling thing and the.
Log m has to be there in the sampling. That's the grouping collector log, right? Like just if you're trying to cover m things, you need to sample like m log n.
This is the conditional expectation version of it.
Yeah.
So just some of the questions.
Yes.
Even in your result, it's conceivable that log n drops off. Because.
Yeah.
And then if you just doing the stream.
You need to do correlated sampling. Like you need to do something like DSS, like some kind of global thing where I don't select. I haven't told you the algorithm, but it's going to be like pick AI with some probability independently.
Okay.
Right? Like you need to do something more global
Mm-hmm.
in order to remove the log n, if at all.
So remove the log n or the log
M.
Yeah, so the log is the log n.
Log of the dimension could be
The log
removed.
dimension could be
Yes.
removed. It's potential that the analysis will be
Yes.
tightened.
Yes.
To do that, to remove the log n, you might need a more global.
Correct. Okay, good. Yeah.
So for the hard instance, or like in general, can I assume that all the AIs have the same spectral now? Like, is that the easy case or the hard case?
It is the only case in some sense. Oh wait, sorry, wait, that's not true. No. No, they could have very different spectrums.
Right, but if I just consider the special case when all of them have the same spectral now.
It's not. No, it's not. No, I don't think.
I mean, isn't it already quite instructive when all the AIs are just Laplacian of matchings, right?
Yes, exactly.
In that case, they do have the same.
Yes.
Yeah.
So what really matters is like the after you take the sum and normalize so that they sum up to identity and take the spectrum. That is the right way to take the spectrum. Before that, it doesn't make any sense. Because I can just multiply everything by. But even then, yeah, like it's not clear that.
So this log n appears even for that.
Yes, absolutely. Yes. Good. Yeah. All right. So let me give you an application. I'm much slower than expected, so it's quite possible I don't give you all the details like I planned, but it's okay. Okay. So
One more question.
Oh, yeah.
Back to the log m.
Yeah.
Look, I understand you want to keep them separate n and m.
yes.
Suppose I give you n is very, very large compared to m. Is
Yeah.
that m actually replaceable by the min of some?
No.
No, you are.
Yeah. So you're asking an interesting question. You're all asking interesting questions. Not my The other way actually has. I came to this problem because of the opposite setting, where little n is very large, little m is actually small, in the sense that I don't mind log little m. I highly mind log little n. In fact, if you could remove log little n here, great things would happen.
Okay.
You would prove the validity lower bound, for example, among other things. But you're asking also an interesting question. It's like, what if like n is small and m is large? Like, what about the other setting? And yeah, all of these are interesting questions, and I have no great answer for any. Yeah, except like, please do it. Okay, great. Let me give you an application so that it doesn't feel like an abstract exercise in theory building. So there are actual applications I came to this at, but this was like the whatever, the one that we could do, and the one that felt simplest without giving me new results for what I actually care about. So anyway, we're clear about this. It's called Cayley sparsification problem. So if you haven't seen Cayley graphs, I'll describe them very soon. But basically, the problem is I want to sparsify a Cayley graph. Right? A Cayley graph, is the following object. You fix a group, right? Just think of, let's say, addition mod P if you want a concrete example. A Cayley graph is described by a set of generators or a subset of the group. And then, all edges are basically shipped by elements of this set of generators. Okay, that's what a Cayley graph is. The simplest example that you can keep in mind if you've never seen this object is the group F2 to the n, the hypercube, and the generators being the standard basis vectors with exactly 1 non-zero. This gives you the usual hypercube as a graph, and that's an example of a Cayley graph on the group F2 to the n with generators E1 up to E little n. Okay, that's one you can keep in mind if you want. So the question is, if I give you any such Cayley graph, can you sparsify it? And of course, I can sparsify every graph in the world, so I can also sparsify Cayley graphs. But this time, I want the sparsifier itself to be a Cayley graph. So I don't want to sparsify edges. I can't sample each edge separately. I'm going to sample from the set of generators. If I keep an edge correspond to a generator, I must keep all of the edges corresponding to a generator or not at all.
So I mean, even bringing this up is difficult. Why should sparsifier of a Cayley graph be necessarily Cayley? That's not clear.
Yeah. So let me maybe say more things about it. So first of all, why might you care about it? So, we care about Cayley graphs because they have algebraic structure, right? Like in many applications, we want not just combinatorial aspects of graph, but we want to deal with algebra, okay? Because let's say, for example, are designing a pseudo-random construction based on it. And then the algebraic properties are useful. So it would be nice if we can like make the graph smaller while preserving the algebraic properties that we like about. That's maybe one high level motivation, right? The other motivation is the following. In some sense, the precursor to graph sparsification is the result that expander graphs exist. Let me explain why. Expander graphs are sparsifiers of the complete graph. They are the ones that approximate the complete graph. And then you can say that, so we have this classical results that there exist sparsifiers with order and edges. There exist expanders with order and edges. So sparsifiers for complete graph with order and edges exist. And then BSS result shows that actually sparsifiers for every graph. So there's a similar result for Cayley graphs. In fact, all of our expander constructions from the algebra world are Cayley graphs, except for the zigzag product. Basically, we don't have a construction, that's combinatorial. But basically, like for expanding Cayley graphs, we do have Cayley graph expanders, right? And you could ask, can I actually similarly sparsify every Cayley? You can think of it as generalization of
every Markov chain sample from a Cayley from a group, right? He is essentially sparsifying the full table, the complete.
Also true.
So that,
Yes.
that permutation would apply to
Yes, for example. Yes. Good. Yeah, does the question make sense? Okay. So
can we expect more of this? That the weights are also have some nice. Is it just the structurally it's a Cayley graph? Because in the complete
I'm going to have weighted generators. So it's going to be a weighted Cayley.
it's a weighted Cayley.
Yeah.
Okay.
Yeah. I can't expect. Yeah.
No, the weighted Cayley graph, but the weight of the edge G and GS is the same for all G. It just depends on S.
Yeah.
The
Yeah,
AI is given away.
Yeah.
The AI matrix is given away.
The generator is given. Each generator gets a weight.
Each generator gets the
Yes, of course.
Oh, okay.
Yeah. You're sparsifying the set of generators. That's what you're doing.
But when there's the generator.
So you're approximating the generating set by a smaller generating set with weights constant. That's what you're doing. Okay. Now, this is just a definition of a Cayley graph. I'll skip it because I gave you definition already. And I gave you examples. So thank you, Raghu. Here's the main theorem we're going to prove using the machinery I told you just now. And we'll come back to it, why you care about high rank and all now. Okay. But basically, we prove that there is a Cayley sparsifier for every Cayley graph with log to the 4 generators. Okay, log to the 4 in the size of the group. Okay. So such a result was known for Cayley graphs from F2 to the N. Also not known for too long. It was a very nice result due to Khanna, Louis Butterman, and Madhusudan from like 2 years ago. And somehow it turns out that on F2 to the N you can make it a combinatorial problem. So you could do combinatorials to prove this. But what we do is now we prove that a similar result actually holds for every group. Okay, except that our bounds are log to the 4 and their bounds are like log of the size of the group times log. So their sizes are actually much better for F2 to the N. We don't know how to prove those results for arbitrary groups yet. On the other hand, before this result, no non-trivial bound for Cayley sparsification for ordinary groups was known. Good. I should also say that there is an independent work, forgetting the author names. I think M is Mohanty, P is Butterman. Also, like Raghu is missing Tim Shea, my student. Age. Yes. My bad. I'll fix. I'll ask Raghu to fix. Raghu's mistake. But yeah. So it's basically exactly the same proof, more or less. And maybe there's there is some sloppiness somewhere, so they got a log to the 5 bound, but basically essentially the same bound, same proof, same result concurrently given by this set of authors. And like I told you, you should think of it as like the analog of the Alon-Reutemann theorem that says that complete graphs have Cayley approximators with log and generators. It turns out that, by the way, you can't expect a constant number of generators here, as you might given the similarity to expanded graphs. On abelian groups in general, you can't expect a constant number of generators to suffice. Log and generators are necessary in general. And you could think of a result as saying that actually log to the 4 suffices for approximating every graph. And in fact, we conjecture that log G is sufficient. We don't know how to prove. Okay.
Do you want to put log G, or if the Cayley graph had the original Cayley graph for generating set D, wouldn't you want it to be log?
No, you can't. Yeah, so it's the same as graph sparsification. Right? I can give you order n size graph, but you can't make it small. Right. So you can give examples that that's not possible.
Okay.
You can only expect log G is in some sense necessary. You can't expect below log G in general. We get dropped to the 4, and the question is, can you get it wrong? I think it's an alpha conjecture to make log believe that.
So in the counter example, go for Cayley graph. So if I give you a Cayley graph with B generators, there doesn't exist a sparsified Cayley.
Yeah, F2 to the n with E1 through E little n has generators.
So because this is capital, okay, fair enough. Okay.
Yeah, like remove any of the graph becomes this kind. Any other question?
So that was the question I was asking. But what your groups in this theorem, they do not have to be abelian.
They don't have to be abelian. Yeah, it works for every group. Yeah, and the proof is exactly the same. So the abelian, non-abelian does not matter at all. Yeah. The one last thing I will mention before moving on to the slide is this is an example of a high rank sparsification. Why? Because if you look at all the edges corresponding to a single generator, they form a perfect match. Okay, so you are sampling. This is like the problem of sampling. All the edges correspond to a generator at once. You either pick all of them with the same weight, or you don't pick them at all. Okay, and notice that if you would have applied the vanilla PSC sparsification result, you get bogus ones. Right? Like the vanilla result says that order n matrices suffice. That's like saying that pick all the generators. That will suffice. So it gives you nothing. So hopefully you see that this instance specific result is actually interesting and important in the sense that it allows you to prove this, where the general one would have given you nothing. Any other questions so far? Okay, great. All right. So how would you prove this? Well, we basically reduce the problem by the main result I told you earlier to bounding this connectivity parameter. And this is an answer to your question earlier, Pranat. Why do we care about alpha? So we don't know how to, even though alpha star equals like whatever, some 0.6 suffices, we don't know how to bound this domination. We don't know how to prove this domination inequality for alpha equals 0.7. But we can prove that if you choose alpha 1 over log the size of the group, okay, then for any Cayley graph, you can bound this connectivity parameter by log n size of the group. So it turns out that we can prove that n star is always at most n alpha divided by alpha for every alpha. So because we prove it for 1 over log n, this gives us a bound of log square on this connectivity parameter. So that's the log square. And then you saw earlier that we lose a log n, log n. Both of them are log n in the second. So that's the log to the 4. Okay? Does it make sense? Okay, great. All right. So, good. Yeah. I think I'll now rush to this next slide to tell you the whole. Okay. All right. So, first round of algorithm. Okay. The algorithm is basically fixed. It's called leverage score sampling. It has been. Yeah. So, it's in some sense the most natural algorithm. It even predates Spearman Srivastava. It actually goes back to Venture Carter. And it's called importance sampling or leverage score sampling. The idea is that, so first of all, even in graph sparsification, uniform sampling doesn't work. You could just choose edges at random, but that doesn't suffice. And the example is already I gave. Imagine 2 clicks joined by an edge, you will never pick that edge. Okay. So clearly, edges have different importances. So what you do is you compute some notion of importance for every edge, and then you sample each edge independently with some probability as a function of their importance. So if it's super important, you might sample it with high probability. If it's unimportant or not that important, with lesser probability. But that's it. It's called importance sample. The importances have various meanings. They are sometimes called effective resistances if you know what those are. They're sometimes called leverage scores if you know what those are, but it doesn't matter. It's a very natural quantity that comes out in input. Okay. So let me tell you what this looks like in the context of our application. Okay. So we are given this family is script A. So A1 through A little m. And an input looks like basically a sum of these subsets, right? A graph. And we want to sparsify this graph with some weights, mu sub i's. Okay, that's our goal. So, we're going to sample each AI with some importance pi, with some probability pi. Pi is like some measure of importance of AI. And, basically, What these PIs are is more or less already in the previous work, in the sense that there is a natural concentration argument, matrix Chernoff argument, that spits out what these PIs are. It's literally like the spectral norm in the normalized sense. Like, make the sum to identity by like normalizing, and then the spectral norms are the PIs. And then, so these are called Leverage scores. And it's actually very easy to show that some of the Leverage scores up to some log n is an upper bound. So the entire goal is to simply upper bound the sum of the Leverage scores. That's it. Right? Like the algorithm is fixed, the analysis is fixed. The only question remaining is what is the sum of the Leverage scores? Okay? Does it make sense? Like if these PIs are the probabilities, right? How many samples would you take? Well, some PIs times some log n to do the union bound. That's what happens. You just have to do the matrix Chernoff and union bound, but it's basically the kind of argument you would not find unnatural. Okay? So the only question I'm saying is like how to bound the sum of the PIs. That's it. Okay. So let's like define this Leverage score carefully and like see what we need to prove about it. Okay. So like I said, we're going to normalize so that the sum becomes identity. Now the sum may be low rank, but ignore that. Okay. Let's assume it's full rank. So normalize and make a tilde I to be, the sum to the minus 1/2 on both sides of AIs. This is just normalizing to the sum is like identity. Sum is like on the same, all eigenvalues are on the same scale, so to speak. Okay. Good. And now, we are going to, so basically we are saying that, we need to sample the sum probabilities from the, from a set of matrices the sum to identity. That's our goal. The score of AI is simply, like I told you.
What are we taking T as? T is just 1 through n.
T is input. T is the input. It's an arbitrary sum. Think of like
the Leverage score with respect to a set that is. Oh, I see.
Right? Yeah. So that's what instance is. I mean, if the instance is a single graph, it won't make sense. Again, like keep in mind the context of graphs. The script A is the set of all edge Laplacians. A given graph is a subset of edge Laplacians. And I'm going to sparsify that. So input looks like T, a subset of script A. That gives me a sum A sub T. I want to keep this sum A sub T while reducing the number of summations.
So in this idea, I misunderstood. I was under the impression that so the little m that was there for standard graphs, I thought was the set of edges.
Yeah, there's M.
That was m.
Yes. What's the input look like? Input is an arbitrary graph, right? That you're trying to sparsify. An arbitrary graph is a subset of edges.
Yeah, I thought that subset of edges was the m.
No, M is all the edges. M is little n choose 2. Like, it's an instance specific property, right? Like, so an instance is described by a set of PSD matrices. An input on that instance is any subset of edges, any subset of AIs.
Yeah.
And I'm going to sparsify that.
So Pravesh, now I'm also a bit confused. Like this capital T refers to it like a tuple of like A1 into A2.
T is just a subset of little m. Just typical example, right? Little m is n choose 2. AIs are all possible edge Laplacians on n vertices, so exactly n choose 2 of them. A graph is a subset of edges, namely T of this little m. And I want to sparsify that graph. And I want to give you a function of this family script A, function of graphs that governs the size of sparsifiers for all graphs.
So because previously T was playing a different role. I mean, because T had this thing where I have a certain family of AIs that I'm trying to sparsify.
Yes.
But the notion of this, what was it, the connectivity thing, that was a function of some T that is.
So when you define redundancy,
Yeah, the redundancy.
I might have overloaded.
Oh, okay. So this T is
I
not.
am
yeah, so in the graph is I mean the score is like that.
Yes. Yeah. Yeah. So, but you don't need to know any of this terminology to understand what's going on, right? I'm saying normalize that the sum is identity, and the spectral norm is the leverage. Okay. And then, just trust me that if you run the trivial matrix Chernoff argument, if you just know the matrix Chernoff bound and you apply it without doing any work, you can read like Akash's notes for it, for example. You can prove that the sum of the leverage scores up to a log n factor governs the size of the sparsifier. Okay, easy. So the entire goal is to bound the sum of the leverage score. Okay. Now, how much time do I have? 5 minutes? Okay, yeah. I'll give you like by the way, the proof is very, very simple. In 15 minutes, I can really tell you the proof, but I'll give you like a 5-minute sketchy version. Okay. So we want to bound, some of these spectral norms of normalized AIs. Okay. And what do you mean by bound? Well, I want to bound it in terms of this qualitative connectivity parameter. I'm going to prove that it's somehow no larger than this connectivity parameter we defined earlier. Okay. So what we are first going to do is like something very simple, very natural simplification. Just like there's you imagine like the spectral norms of AIs are like arranged on this histogram thingy. Let's just bound what the sum of these spectral norms is of all the terms that have spectral norm at least eta. Like what's the contribution of bars which are higher than eta? Then I I just sum it over all etas and that's my sum. Does that make sense? The natural way to do Riemann integrals, if you will. Like it's a way to like you partition it, it's like, okay, how much is the contribution of things larger than eta over 2, and so on. Okay. So just this just fixes the scale in some sense. That's why I'm doing this. Okay, good. So we want to understand how many elements. This reduces to a counting problem. We want to understand how many elements, how many AIs have spectral norm at least eta. What's the size of S eta? Okay, good. So what we're going to prove is that the size of S eta can be controlled in terms of this connectivity parameter, namely that it's no more than the connectivity parameter over eta. Like this alpha is a constant. Okay. Okay. And now you can basically integrate this if you want and lose a log n factor, and that's the sum. So the entire goal is now to understand what's the contribution, what's the number of elements in S eta. Okay, good. So again, like a very, very proof sketchy version, I'll say. So we're gonna do S eta. So now in S eta, every AI has spectrum of at least eta. Okay, what does that mean? There is a witness vector, there is a quadratic form on AI on some vector Wi, such that the Wi transpose AI Wi is at least eta. Right? Now Wi is going to be different for each AI. It's not the same. It's just the witness for that AI. Okay, good. Now imagine that I could somehow also ensure that if I look at the quadratic form on AJ of the witness vector for AI when I doesn't equal j, then this contribution is small. Okay, so for each AI I have a Wi on which the quadratic form is large. Further, imagine that the sum of the contributions from Wi, the quadratic form, on the rest of the AJs happens to be small. Okay, then notice that I can bring back my connectivity parameter into play. Right? What was the connectivity parameter? It was like, I need to dominate one by the sum of the rest. Okay. Now look at, and this means it has to be true for every quadratic form simultaneously. So if I had a Wi, right, for AI, and I want to dominate AI by, the rest from the rest, but the contribution to this quadratic form on Wi from the rest was small, then this domination inequality cannot hold unless I have two large enough. So this basically gives me so this is a contradiction because I know it is bounded. So it tells me that I should be, if I could somehow ensure that this witness vectors have this small cross contribution property, I would be able to bound S eta with the connectivity parameter. Does it make sense? Just intuitively speaking. You won't see the quantitative thing, it's not hard, just time-wise, okay? So the only question is how do I ensure this? It's very easy. It turns out that you can just sample from S eta and ensure this property. Okay? Let me give you one line reason why you should expect that. Remember that now this is the reason we restricted to AIs with spectral norm at least eta. The sum of the spectral, the sum of the quadratic forms in direction Wi cannot be more than 1. The whole thing sums up to 1, identity. So there can be only 1 over eta different AIs in the direction W that are large in the direction Wi. So if I sample at the rate eta, I should expect only 1 of them to show up. Okay? So what is it saying? If I look at S eta, sample at the rate eta from it, I should expect every direction to basically, have 1 of the large things show up, everything else will be small. And so I should have this small cross contribution property. That's it. That gives me the 1 over eta times the connectivity parameter. And I'm only lying slightly to say I don't need to work too hard beyond what I just told you to complete the proof. Okay? But that's all I will tell you. I don't know what Raghu wrote, but I gave you the proof.
Can you go to that intuition one page?
Yes. Intuition 1 page. Go, Raghu.
This one, the book. So in the previous page, you have a bound on the eta, right?
Yes.
Yes, it should be n star, right?
Yes, yeah, well, it's really true for, so n star is just, the value of n alpha comma a at some fixed constant alpha star. We are saying that actually I can bound it for every alpha, I can bound it by n alpha a over alpha a. When you plug in the value of alpha star to be some fixed constant, you just get, a bound in terms of n star.
No, I thought that the N star is on the uniform one, like the uniform is not the aim.
What do you mean uniform?
So I mean to say, when you choose the A, when you define the A alpha eta,
Yeah.
you took a particular subset of
No, it's for all one.
It's a bound that works for every subset.
It's like, remember the graph case. Every collection of n edges has a redundant edge. That's like, this is the analog of that property. Every collection of n alpha a elements out of script A has redundancy in the sense that one of the AIs can be dominated by some of the rest. But yeah, so I maybe just not say anything more here. I'll skip this part and end with the open questions. So the proof for by the way, I skipped the slides for why the n star in the case of Cayley graphs is what it is, log square, like I promised you. But the proof is also very simple there. I'll just give you a one-line teaser, and then you can actually, I guarantee you can, if you think for 1 hour or something, you will be able to feel the proofs too. The simple observation is that if I look at any group, okay, and think about all possible. So look at more than log of the size of the group generators, okay, and look at all possible words you can form on the group with the generators, okay. Then just by counting, two different words must collide, must have the same value, okay. This is the analog of cycles in arbitrary groups, okay, and you can use this observation to prove this bound I told you. There is nothing very mysterious going on. It's simply saying that if I take at least log n generators and look at all possible words, like all possible subsets and their products, then there has to be two different subsets which have the same product. Just some pigeonhole argument. Okay, that's it. Okay, by the way, this kind of a quantity is actually very well studied in group theory. It's called the maximum size of a minimal generating set of a group. And it's a result. It's not a hard result, but it's a result that says that it's never more than logarithmic. Okay. So you can just simply say that what we do for Cayley graphs is we reduce the sparsifier size to the maximum size of any minimal generating set of group. That's what's happening, and it happens to be log n. Okay. Okay. So the natural open question is, one, is the log n factor necessary? Can you remove it? Can you somehow do BSS or MSS to do it? Right? And two, for Cayley sparsification, this application in particular, can you get logarithmic bound? Okay. For abelian groups, you can't expect anything better than logarithmic. And so the natural question is, can you match it? Maybe it comes as a little bit of a surprise in the sense that there are non-abelian expanded graphs, Cayley expanded graphs, with just constant number of generators. In fact, like the journal research has shown that when groups are so-called quasi-random, then such expanders always exist. Okay. So you might have expected that if I go to sufficiently non-abelian groups, let's say as measured by the dimension of the minimum irreducible representation, you might expect that I can do something better here. Okay. Turns out you can't, in the sense that for every group, there is a graph, there is a Cayley graph that requires at least square root log number of generators to sparsify, and it's not a hard result. It's simply that every group has a abelian, an embedding of an abelian group of some size, and you can use that result. Okay, so yeah, somehow it's a little bit different from my ideas in the context of graph classification, where you could get constant size or whatever, constant average degree. Here you can't expect to get that even for extremely non-abelian things. All right, okay, that's where I will stop. Yeah, sorry for going on. Questions?
How do these parameters sort of tensorize in the sense that if I was asking the same question, I mean, like for example, I would like to understand a certain parameter for a given generating set for a group G.
Yeah.
I will just think of the group G power k, where k is a large enough number, and take the generating set to be the natural generating set. And
yeah, very good question. I haven't thought about this.
because the statement you were making saying that the redundancy is a state like saying the conversation of this particular generator can be captured by words of a certain length. If that's the statement I want to make, it somehow felt like you are looking at a.
Yeah, so it's a good question. It's a natural question, but I haven't thought about it. What would be the answer in the hypercube? My guess is that basically you should expect that to happen.
No, the thing was because especially the part where you're able to prove a bound where your alpha parameter is like 1 over log n.
Yeah.
Whereas you only want alpha to be a constant. Right?
Yeah.
You don't need a 1 over log n. So I was wondering if you
Can you do better by like cancellation?
Yeah,
Right? That's what you're saying. No, it's yeah. So yeah, I don't know. Yeah, but it's a good question. I'm gonna think about it. Maybe I can.
So, this is a bit of a stretch, but I mean, there is this result by like Rasmus, Cayley and Johnstone, where in order to specify a graph, what they do is when they say that, just keep a bunch of random spanning trees, like log n many of them, and that will be a good structure specifier.
Yes.
So, like, is there an analog that one could imagine here?
Yeah, I don't know. In some sense, I would, or I guess this, I'm skeptical just because there is a lot more algebraic structure and then it's not clear that there are objects like spanning trees and all.
Yeah.
That makes sense here, right? So yeah, I don't know. Yeah.
Any question that you actually know?
I have that one. Yes.
Yeah. Going back to the M.
Yes.
M can always be assumed to be almost poly if you can, because you could replace summation AI with just polynomially many guys here, and so it doesn't.
No, why? Or I guess how?
Because it's in the convex combination of the.
Yeah, but you need, you have to maintain.
You just replace summation AI.
No, but
You just replace summation. There are several M's. You just write A summation AI. The thing that you're sparsifying is just the sum of. You're deciding in N square dimension, so M can be at most N square.
Yes,
On the other end, M is at most N square. Now suppose out here for this Cayley graph, starting Cayley graph was a Cayley graph with the number of generators being log G.
Okay.
What is your
Nothing.
Nothing, it won't give you.
Okay.
But do you expect anything to happen, or because of the comment you said last, square root log G?
Yeah, like hypercube. Like let's say my graph is hypercube.
No, the number of generators is log.
Take a subset of exactly.
Oh, okay.
Disconnected graph. Just like take the first, whatever, log little n generators, E1 to E log n.
Yeah.
You need all of them. Like you can't expect to remove any of them.
No, you need all of them, but your thing is actually putting even more the Cayley graph that you're getting is not log G generators, it's actually giving you log G generator. That's my question.
Yeah.
So
if you have less than that, then it's trivial in the sense that there is nothing to sparsify, right? Like in some sense the theorem is really.
No, I'm asking what happens when M is really small. Do you when M is really tiny?
So there might be a way to ask this question in an interesting way.
If
you allow arbitrary M, then I'm saying that examples would forbid you from doing anything. Right? Like you would create examples where some part literally becomes 0 because you dropped one of the generators. There might be a way to, I don't know, maybe I can't think of one right now, so another question that I don't know. But there might be a more intelligent way to ask that question, and then maybe an interesting answer.
You can put the onus on me.
I'm really excited doing that. Yeah, and I'm glad that there are so many questions because this talk is entirely about questions. Basically, the answers were not that many. Raghu is not wrong.
All the first time. Let's sign him again.